Good morning, welcome to important results in Fourier Transform. In this short video, we are going to discuss more important results related to evaluation of Fourier Transform. The first important result is Fourier series expansion that we have discussed in semester 1. That is actually the core part of Fourier series analysis. The second part is odd and even function. Why a function is called odd, when does a function is termed as even, then what is the geometrical importance, then what is the use of this odd and even nature in evaluation and integration, and finally we will discuss some important results from integration. So the Fourier series expansion is writing a function f with a period 2l as sum of cosine and sine. That is fl of x equal to a0 by 2 plus sigma n equal to 1 to infinity n cos omega nx plus bn sin omega nx. In the previous class we have learned this omega n as pi n by l. Omega n is actually pi n by l. We call this pi n by l as omega n for the transaction easiness. Here this a0, an and bn are known as the Fourier coefficients, and they are calculated using the Euler's formulae. A0 is equal to 1 by L integral minus L to L FL of x dx. An is equal to 1 by L integral minus L to L FL of x cos omega n dx. Bn is equal to 1 by L integral minus L to L FL of x sin omega n x into dx. It is not that this Fourier series expansion for this function is valid only if this function is periodic with period L and it satisfies the Dirichlet's conditions. Dirichlet's conditions means some of the desirable properties for this function to have a finite integral representation. So even and odd functions. A function is even if it is symmetrical about the y-axis. A function is odd if it is not symmetrical and it is actually flipped reflection. This positive side, we take the positive side, then take the flipping and take the reflection, we got the same portion as in the positive side. That is odd and even functions. We are going to define this odd even function mathematically like this. A function f of x is called even if f of minus x equal to f of x. That means this function gives the same graph for positive x and negative x. That is, it is symmetrical about the x equal to 0 line or y-axis. Geometrically even functions are of the form y is equal to f of x are symmetrical about x equal to 0. That means y-axis. Example for these even functions are even degree polynomials like x square, x raised to 4 etc., x raised to 2n, then cos x, sin square etc. For example, I will show sin square x, it is even. Sin square x is an even function. The procedure is start sin square x with f of x. Then I replace x by minus x. So left side f of minus x, right side sine of minus x the whole square, because sin square x is sin x into sin x, that is sin x the whole square. I write in that way, then put minus x. Then sine of minus theta is minus sin theta, so minus sin x the whole square. Minus sin x the whole square means minus sin x into minus sin x, that is sin square x. So f of minus x is f of x itself, so it is an even function. It is not that sin x is odd but sin square x is even, because sin x is odd function because sin of minus x equal to minus sin x, but when we take even power it automatically come to even function category. Now we discuss what is an odd function. An odd function has the definition f of minus x equal to minus of f of x. Geometrically, even functions of the form y is equal to this odd functions are of the form y equal to f of x are flipped reflections about y equal to 0. For example, odd degree polynomials like x cube, x raised to 7 etc., and sine function, and also odd powers of odd functions, sine raised to 3x, cos x by x. Here cos x is an even function, x is an odd function. So even function by odd function and even function into odd function all are odd function. In order to remember these properties, we can use an analogy. Cos x is an even function, so we usually denote even function by a positive sign and odd function by negative sign. So using sign notation, Cos x is even, so it is positive, divided by, this is x raised to 1 odd, so minus. Positive by negative is always negative, and so cos x by x defines an odd function. We will prove this. We start with f of x equal to cos x by x, then f of minus x equal to cos of minus x by minus x. We replace x by minus x. Cos of minus theta is cos theta, but minus of x is minus x itself, so I can take this minus outside common, so cos x by x is f of x. So f of minus x equal to minus of f of x, and so this function is odd. So odd function has positive side and negative side. The positive side and negative side are in opposite direction. That means if we think it in term of area, the positive side of x gives the positive area, and the negative side of x gives the same area but in negative direction. So when we add up this both the area, we go to 0. So we integrate from minus a to a of this function. Odd function gives area get cancelled, so we go to 0 area. But in the case of even function, when we take x from minus a to a, the right side area and left side area are same because it is symmetrical about the y axis, and hence in order to find the total area from minus a to a, it is enough to calculate area from 0 to a, then take 2 into that part, that is double that area. That is the importance of, or that is the easiness when we are using this odd and even nature in integration. Okay. So role of even and odd nature of function in integration. We can use this property in evaluation of integrals with the symmetric x range about origin. That means from x equal to 0, it takes minus a to the left and a to the right. So it is symmetrical. This x value is symmetrical about the origin. This is an important theorem. Integral minus a to a, that means minus a to a, it is symmetrical about x equal to 0. F of x dx equal to, if its function is even, as I already told you, it is 2 times integral 0 to f of x dx. But this function is odd, their area are in the reverse direction. So one is in positive, other is negative. So when we sum this, that means we integrate or bring it together, it gives 0. So it is easy to remember, odd function is like odd man out. Its total is always 0. Even function is a good function, its effect is amplified. That means 2 times integral 0 to a f of x dx. It's simply an analogy to remember this result. Integral a to a f of x dx is equal to 2 times integral 0 to f of x dx. The function is even and it equal to 0, the function is odd. These are some important results from trigonometry that we are extensively used in evaluation of integrals associated with the Fourier integral representation and Fourier transform. Sin square theta is equal to 1 minus cos 2 theta by 2, and cos square theta is equal to 1 plus cos 2 theta by 2. Then 2 sin t cos t is sin 2t. Then these are some formula, and this cos a plus b can be expanded as cos a cos b minus sin a sin b, and cos a minus b is equal to cos a cos b plus sin a sin b. Sin a plus b is equal to sin a sin b plus cos a sin b, but sin a minus b is equal to sin a cos b. This plus is changed to negative. So you should write down this formula in your notebook, and it will keep it as a ready reckoner or an easy reference, because we have to use these results to evaluate integration. The main thing is that Fourier integral representation and Fourier transform consist of a lot of integration, and in this integration either a cos function or a sine function is multiplied with the given function f of x, like integral sum minus infinity to infinity f of x sin ax dx, or integral minus infinity to infinity f of x cos ax dx, like that. So a product inside the integral is there. Integrand is a product. So we have to use either integration by parts or any of the results to bring it into a sum. So these results are mandatory in the case of Fourier integral and Fourier sine cosine integral representation and also Fourier transform. Now we move on to an important integration result that is called the Kronecker rule or Leibniz integral. This rule is actually for integration by parts. We are going to apply integration by parts in a special way if this integrand has some peculiar nature. If in the integral uv, the first term u, so we can rearrange these terms. If this first term, instead of this first term u, v has the characteristics, we put that v into the first term. There is no problem. The first term u is a polynomial in x. That means the integrand is a product, and one term will be a polynomial expression. Then we can evaluate the integral using following rule. Integral uv is equal to, original rule is integration by parts, that is u into integral v minus integral u dash into dv. Instead of that, we can use this result provided this first function is a polynomial in x. So we start like integration by parts. First into integral of the second term minus. Now you look into this expression. You take derivative of the first term, that is u dash. Integral of the second term, double integral v. This is minus, next term is positive. Now look into this term. First term is u dash, its derivative is u double dash. Second time is double integral v. Now we take one more integral, that is triple integral v. This is plus, next is minus, like this. It is interesting to note that this u is a polynomial and we apply differentiation successively. After some stage, the derivative becomes a constant and in next stage it will become 0. So these terms will terminate after finite number of steps. That is a hint here. After a few terms, derivative of u being a polynomial will become 0. So the integration in the RHS will terminate in finite number of steps. That is the idea. Now, these four results are very important in Fourier integral representation. The first one is integral e raised to x sin bx dx is equal to e raised to x divided by sum of squares of this coefficient a square plus b square. Then put a long bracket, then a into sin bx as itself. Then actually there is a plus, then we take this b into integral of this sign. Integral of sign is minus cos, that is minus cos. So minus b cos bx. So in the similar rule we can do this, integral e raised to x into cos bx dx equal to, as usual, e raised to x divided by sum of squares of coefficients, that is a square plus b square, then a long bracket, a into cos bx as itself plus b into integral of cos is sine, so b sin bx. Another result is integral 0 to infinity e raised to minus x square dx, it is equal to root pi. We got this result from gamma function. And second one is integral 0 to infinity sin x by x dx, that is equal to pi by 2. The sin x by x is called a sinc function. Integral of sinc function from 0 to infinity gives pi by 2. We have already proved this result using Laplace transform. Once again we will show the same integral in Fourier transform. So these are all important results as far as the Fourier transform and Fourier integral representations are concerned. So you should write down these results into your notebook and keep it as a ready reckoner whenever the Fourier transform or Fourier integral problems come to vogue. Okay, thank you very much.